Today let us start by getting some practice in the art of writing the bond graph and assigning the power duration and causality. Let us start with this problem. Suppose you have got a mass. Mass is acted on by a force F, and here we have a spring damper arrangement connected to the ground, and suppose at this point we have a lever, and at the other end we have a spring and a mass. And say the ratio is A by A and P. So, if that is the system description, we can say this is K1, this is K2, this is R, this is M, and so on and so forth, M1, M2. I suppose we have given everything. So, how we would write the bond graph for this? In starting to write, let us start from this point. We have got a source of effort sharing the same flow with the mass. So, we will put a one junction, we will put a one junction, and connected to it there would be the SE element, connected to it will be the I element. So far so good. What is there? At this point we have what? A spring damper arrangement which is sharing the same effort between the top and the bottom. So, we had earlier done it by two means, one in which we have a 0 junction connected to a C, a 0 junction connected to an R, but that is also connected to something. It shares, these points share the same flow with what is this ground? It is also a source of flow which is 0, right. So, the ground which is not moving means that it is imposing a specific flow on this point, which can be represented as SF, sorry, 1 SF. Now, this is equal to 0, we understand that. Fine. Then connected to this we also have this point, and this point is sharing the same flow, this point is sharing the same flow with the mass. So, that should also be connected to this one junction. So, we have this bond. This bond is representing the rest of the system, right. Now, what is there in the rest of the system? We first have a transformer. So, this is a lever which is the mechanical transformer. So, we have to represent that, as we have told in the last class, by a transformer element. Now, this transformer element, what we will have to assign its transformation ratio? Yes, it should be minus B by A. B is in this picture the other side. So, minus B by A. So, it has gone to the other side. We have actually come to this point. So, the flow here in this bond is nothing but the up and down motion of this one. So, this point and this point share the same effort. This point and that point share the same effort. So, they should be connected by a 0 junction connected to the C element here, right. And then we have this point and the M2, they also share the same effort, or this point and that you can also think that it is connected by one junction to the I. Now, notice that this one junction actually is a through junction. We had argued that this point and the mass share the same flow, that is why, but actually it is a through junction, nothing, there is nothing other thing connected to it. So, we can simply connect it directly, because if it is a through junction, then effort and flow here must be equal to the effort and flow there. So, there is no point in putting a junction at this point. Notice a few other things. Here the source of flow is 0, which means this bond carries no power. If this bond carries no power and here is a one junction, this is the flow is 0 here, one junction will equalize the flow, which means in these two bonds also the flow will be 0. If the flow in these two bonds are 0, then obviously the power is also 0. So, if power is not flowing, there is no point in putting the bonds, right. So, this part is actually unnecessary. The moment you have this part unnecessary, these become through bonds, this effort and flow should be equal to the effort and flow here. So, there is no point in putting this also. So, that significantly simplifies. So, let me freshly draw it in another page. We have got a one junction connected to a I element, we have got a AC here, here there would be a C, here there would be an R, here there would be a TF connected to the minus B by A, you have got a 0 connected to a C connected to a I. So, that becomes the bond graph. Fine. Is that well understood? Okay. Now, let us assign the power directions. In assigning the power directions, we first start from the source, its power direction should be like that. So, its power direction should be like that. There is no other source. So, we now choose the individual elements and give the conventional power direction. Fine. There are two bonds which are between these. So, again we can any way we can do that, assign the power directions, but you can see that the power source is only one. So, the power should actually flow in that direction. So, it becomes natural to assign these directions. For the transformer element, if the power comes from one side, it should be going to the other side. So, it should be like that. Again, it is perfectly fine if you choose to do it opposite, this direction, that direction. Only thing is that the positivity of the specific things would be different, but let us not worry about that at this stage. Yesterday we talked about the causality, and let us worry about that now. How should we go about assigning the causalities? First, let us start with the sources. We have got a source of effort here, and we know that its causality must be like this. That means, it gives out the effort information and should be receiving the flow information. So, it is like this. So, the causal stroke should be there. What about the I element? I element is one that naturally receives the effort information and gives out the flow information. So, it should give out the flow information. The moment the flow information has come into the one junction, that one junction will distribute the flow information. It is a flow equalizing junction. So, immediately the other things attain these. Okay. Now, here you have a C whose normal structure is that it receives the flow information and gives out the effort information, and which it is doing. So, we are happy. R could do both, but in this specific case it is receiving the flow information and giving out the effort information. So, ultimately we have come to this bond. In this bond, I can see the flow is going flow is flowing this way, flow information is going that way, this way, and naturally the transformer element, the flow here is a constant times the flow here. So, the flow information should be going that way. So, it is like this. We have come here and there are two things connected to it. It is a 0 junction. Let us first causal the C. C is the C elements natural causality is that it receives the flow information and gives out the effort information like this. 0 junction has already received the effort information. Therefore, it should now distribute the effort information, which is already doing in this bond, but this should also be distributing the effort information, which is like this. You can see that I also gets properly causal. I should normally receive the effort information and give out the flow information, which is correct here. Clear? So, that is how we assign the causalities. So, while I was assigning this, I was speaking and elucidating the line of argument. If you tend to forget, just write that down, otherwise later it might be a bit difficult to recall. So, the logic was that we started from the sources, then we went to the individually the storage elements I, C and all. The moment one storage element is connected to a strong bond, that means a one junction, if one bond is bringing in the flow information, it is a strong bond. Here is a strong bond. Similarly, here is a strong bond. The moment you have that, the others become automatically determined and you do not have to bother about the rest of the things. Okay, let us do another problem. Again a relatively simple problem, but should be illustrative. Suppose you have a circuit in which you have got a let us do the DC machine problem. So, here you have a DC machine. Imagine that it is a constant field, it is a constant. The machine should have its armature inductance and armature resistance. Fine. And the machine is connected to a shaft, and say the shaft is connected to something that rotates, a mass against some body. So, now if we assign the names to different things, this will become the inductance of the armature, this is the resistance of the armature. Okay, these two things should be there. This rotor should have its own inertia. Let us assign that as I1. There should be a bearing and the bearing should have some friction. So, at this point there should also be a friction. Now, we have the shaft here. Now, this shaft normally should have some kind of a freedom. So, these two ends are slightly able to move independently of each other. So, you have some kind of a springiness represented by a spring constant K. This fellow should have its own inertia and these points should have its own friction. Okay. Good. At this point we can start. Okay, there is a applied voltage which is say E. Is a DC applied voltage. We assume the flux to be constant. Okay. Now, let us start. We start from this source of effort here. So, we have S E connected to a bond. This S E shares the same flow with these two elements. So, it is a one junction connected to, there will be two things, one an I element which is this is AC element is the E applied voltage, there will be R fine. Now, then what? This is also connected to something. Imagine the electrical circuit, what does it see? It sees a back EMF here. So, this back EMF is created by the electromechanical action, and as we have understood that this electromechanical action is to be represented by a gyrator. So, here is a bond which is connected to a gyrator. Okay. Let's try to understand. This bond, its effort should be the back EMF. This side is mechanical side, effort should be the torque. So, here the flow should be converted into the torque here, and here the back EMF should be converted from the speed here. And we know that T is equal to K phi IA, IA is the current flowing here, current here. So, the transformation ratio is K phi, right, and we do not need a arrow in this case in gyrator, because in both the sides the transformation ratio happens to be the same. Okay. So, we have come to this side. In this side what do we have? This point and that point share the same effort. So, it is a 0 junction to which we will connect a C element which is our K. Now, that is connected, this side is sharing the same flow with this mass and the frictional element. Okay. The frictional element is seeing the same flow as what is being seen by the mass, as what is being seen by this end of the spring. So, we have all that connected by means of one junction. So, what do we have here? We have an I which is I 2, where is I 1? Oh, we have missed, sorry, this point we have missed. No, then just let me do that once again. We will have this picture here and we will do that. SE connected to a one junction, connected to a I, connected to a R, connected to gyrator. So far so good, is fine. But after that we have this first. After that it is connected to that. After it is connected in converted into torque, the torque is applied first on the I1 element. So, that there has to be a one junction connected to a I and connected to another R, these two. Now, then that one junction here, it shares the same flow with this end, but this end and that end, the same logic then continues, 0 to a C, 1 to I, R. Okay. Is that clear? So, let us now assign what is what. This fellow is our E, this fellow is our LA, this is RA, this is I1, this is R1, this is K, this is I2, this is okay, and this is fine. Let us assign the causalities. let us assign the power direction first. We will let it go this way. Okay. So, the first part done. Now, we need to assign the causalities. Let us start with the AC. AC is something that gives out the effort information and should receive the flow information. There is no other source. So, let us come to the next storage element, this one, which receives the effort information and gives out the flow information. So, the flow comes this way, it is a one junction. So, this becomes a strong bond, bringing in the flow information, the other bonds must distribute. Here is the gyrator element, which has here the flow is going, and therefore, the effort should be going. So, the stroke should be here, effort should be going this way, means flow should come this way, and therefore, the causal stroke should be there. We have come to this one junction, and here is a storage element I, whose natural causality should be like this. So, this again becomes a strong bond, because it is a one junction, it has already received the flow information, it should distribute like this. So, we have a 0 junction in which a flow information has come, that means that it is not yet complete. There has to be a effort information coming into this 0 junction. From where does it come? The C, like this. The moment the effort information has come, it has to be distributed by the 0 junction like this. And then I have a 1 junction in which here is the effort information coming, and therefore, it is not a strong bond. Here has to be the strong bond, because this fellow is a I junction whose causality like it should be like that, and this brings in the flow information, which then must be distributed, is already distributing this side, and this fellow should also be distributing. Okay. That completes the story. Fine. Okay. Now, after having understood this much, if you have any question about this, please ask. This is the right stage to ask. If not, let us go ahead. When referring to these elements, we have been saying that these are the natural causalities. What do we mean natural causalities? What we meant is that for the I element, the natural causality is one, where it receives the effort information and gives out the flow information. Receive the effort information in what sense? In the sense that we can write the flow is equal to something times the integral of the effort, sorry, so this is integral over the history. Fine. Therefore, the effort is the cause and the flow is the effect, and that is how we say it is a natural causality. Now, there can be certain situations where you will not be able to assign the natural causalities. Imagine that you have a current source and an inductor. How will you draw the bond graph? It is a SF I 2 sorry 1 to I. Power direction, no problem. Causality, SF is the element that gives out the flow information. Therefore, the one junction should give out the flow information, and see the I element now receives the flow information. Here we have a problem, it is not integrally causal, right. So, here we have a problem, and in such cases we will say that it is a differential causal. It is differential causality here, because the integral relationship that we wrote here will not hold in this case. Why did this problem happen? Can you physically understand this? Because the inductor is an element whose natural behavior is that it receives the effort information, gives out the flow information, but here it is connected in series with something that imposes the flow on it. Therefore, it is not able to determine the flow independently. That gives rise to the differential causality. Okay. Let us try to figure out another situation. We have got, say, a voltage source connected in series with a capacitor. Not difficult to say that it is going to give rise to the same problem. So, instead of doing that, let us do something that will make the picture a little more. Normally, if you get such a circuit, you will not see any problem with it. Let us draw the bond graph. Bond graph would be a parallel junction. So, it is a 0 connected to 4 bonds. In this side it is SE, here it is C, here is I, and here is R. No problem in assigning the power directions, but here we have, when we try to assign the causalities, SE element is one that gives out the effort information, receives the flow information, and the moment the effort information has come to the 0 junction, all the other bonds should be taking out the effort information. So, their causality should be like this. For this one there is no problem, because it is receiving the effort information, giving out the flow information. For this there is no problem still, but for this there is a problem, because now the C element is receiving the effort information and giving out the flow information, which is not its natural causality. So, this is also a differential causality. Understood? Now, let us get to the point. The point is, we have already said this when we were dealing with the graph of electrical circuits, that whenever there is a loop containing only voltage sources and capacitances, we had a problem, right. At that time we have dealt with this situation. Whenever there is a loop containing only voltage sources and capacitances, then the Kirchhoff's voltage law would say that there is at least one capacitance which is not independently determinable. So, that situation is leading to a differential causality. Okay. Similarly, we have also learned that if there is a cut set containing only current sources and inductances, a cut set anywhere in this whole circuit containing only current sources and inductances, that is going to give rise to differential causality in this case. So, what we have understood there, as a particular element, it is not being able to determine its own, or it is not free to determine its own state variable. So, that we saw that there these elements did not give rise to a state variable. These elements were, what did we do at the time when we were dealing with graphs? We said that okay, we will draw the standard tree, and only the capacitances that appear in the standard tree will be the ones that will create a state variable. So, therefore, we saw that some capacitances may go out of that definition. We saw that some capacitances will not produce state variables, it is this. Okay. So, in bond graph terminology, the equivalent of that kind of a situation is the differential causality. When can differential causality occur in a mechanical system? In a mechanical system also, if there are two things which are apparently different, but they are not independently able to decide their own state variables, then that will lead to a differential causality. Imagine we have done this problem. Okay, let me draw once again. We have a mass, we have this arrangement connected to the ground, and we had this, and we had a, at this point suppose the other mass is directly connected to this. Let's do the bond graph of this. Here we know that it is a one junction that is connected to the SE, connected to the I, and connected to these two. We have already seen that, so we will not go the long way. C R, and here is a transformer connected to, in this side what? In this point, so the flow here has come to this point, and this fellow share the same flow, it is a I. So, let us keep this through junction for now. So, the power direction should be like this, there is no problem there. Let us try to assign causalities. Here there is a AC element which should be causal like that, and I which should bring in the flow information. The flow information has come to the junction 1, and therefore, all the other bond should take out the flow information, and the flow information now has to travel through the transformer element. So, it should be causal like this. The one junction has already received the flow information, and therefore, the other end should take out the flow information. So, the I element is now differentially causal. Can you see that? So, it is a differentially causal because the other side of the system, that is forcibly determining its velocity, and this fellow is unable to decide its own velocity. That is why it has become, this particular element has become differentially causal. Fine. Is it clear? Good. So, there may be a few ways of getting rid of this problem. One, you could say that no, let us make it a bit flexible. The moment you make it a bit flexible, it becomes proper integrally causal. Say in this problem, how can you get rid of the differential causality? Simple, as you have bit of resistance here 0.00001, then also it becomes proper. Just check that. Then this point has freedom of choosing its own voltage. Or you can also check that in this problem, if this shaft is stiff, which means that there is no freedom of motion in the two sides, then also it will give rise to differential causality. That is why we had put some stiffness here. Okay. Now we are in a position, once we have done enough practice, understood the details, now we are in a position to write down the differential equations. Now, the differential equations writing process, as I told you, is a somewhat algorithmic process. So, let us talk about that algorithmic process. First, what are the state variables? The answer is one for each So, for every integrally causal storage element there will be one state variable, and this is important because if there is a differential causality, that particular element will not produce a state variable. That becomes somewhat standard. So, what are the state variables? There will be one, all right. Which are the state variable? That is, for the inductive element, what is the constitutive relation? P dot is equal to E. P is the momentum, right? Simple equation. Rate of change of momentum is nothing but the effort. That is the constitutive relationship of any inductive element. So, this tells you that the momentum should be the associated state variable, then the equation should be simple. That is what we have also understood or realized when we talked about the Lagrangian formalism and Hamiltonian formalism. Momentum is the right state variable for the inductor. For C element, we would like to express the right hand side in terms of the effort or the flow. These are the variables that we know in bond graph. So, in the right hand side it should be the flow, in the left hand side it is the simple Q dot. So, the charge in the C element is the natural choice of the capacitor. That is what we did earlier when we wrote the equations with the help of the Lagrangian methods. So, the whole thing is consistent, it is only a different language in which we are doing the whole thing. Fine. So, we have which means that for the I element the momentum is the choice of the state variable, for the C element the charge is the choice of the state variable. And for every integrally causal I element there should be one P, for every integrally causal C element there will be one Q, clear. So, the choice of the state variable should be clear from this. Next, we ask exactly two questions, and the moment we answer the two questions the equations come out, simple. So, what are the two questions? First, so every element actually gives something to the system. First we will take stock of that, what does each element give to the system, and second, second question is related to only the state variables. These are the two questions. See, the integrally causal storage elements, in this case you can easily see that the I element receives the effort information, C element receives the flow information. So, the right hand side is what these things will tell. If you can express that in terms of the other state variables, you get the differential equations, but in order to do that we need the answer to this question. Let us illustrate with the help of one example. Let us start with the mechanical example that we have already seen. For this one we have already written the bond graph as this. Again I am just repeating, I am not deriving the whole thing because you have already done that. Here there would be a 1 junction connected to a SE element, connected to an I element, and here it is connected to a 0 junction, and the 0 junction is connected to a 1 junction, connected to C, connected to R, and this is connected to here there is a SF element. Notice the logic that here is a 1 junction, and that 1 junction is distributing the same flow in all the sides, and that is exactly what is happening. What are sharing the same flow? This AC element, the M, and these two ends, right, and whatever are at this end and the whole end, they are sharing the same effort, and that is why we have connected the top and the bottom through a 0 junction. And then we are starting to worry about what is in between, and what are in between this friction element and the compliance element, they share the same flow, they have to move together. So, they are connected by a 1 junction. So, that was the logic. Now, let us do the power directions and causality. It is like this, like that, like this, that, this. The other things can be assigned any direction. So, how do we assign it? We can assign like that, and since the AC element is top there, we can, of course, you can give both the causality, both the directions, power directions, this way or that way. Let us give just this. Source of flow. Oh, sorry, yes. Yeah, it's not that. Sorry, this is not right. It should be giving power into the system. That's source of flow. Okay, now let us assign the causalities. SF should be giving flow information into. SE should be receiving the flow information. I should be giving the flow information, and this fellow should go into the 1 junction, and therefore, it is already receiving the flow information, it should give here. Okay. So, you have this junction bringing in the flow information, but as yet nobody has brought in the effort information, somebody must. So, it is like this. This fellow is bringing in the effort information. So, it has already brought in the effort information that way, and flow information has flown this way, 1 junction. Therefore, it must distribute the flow information. Okay. Now, give them numbers, simple 1, 2, 3, 4, 5, 6, 7. Okay. Now, once we have given that, now let us start asking the questions. What were the questions? What do the elements give to the system? What do the elements give to the system? We have many elements. So, we will ask this question with respect to each element. Okay. 1. Here is an element I2. What does it give to the system? The flow. It gives the flow. So, it is F2. So, F2 is the flow is in terms of state variable, right, pretty simple. So, we have I2's answer is obtained as this, it gives F2, which in the right hand side we have expressed in terms of the state variables. P2 is a state variable in this case. So, let us write What are state variables? One, you have this as the integrally causal thing, this as the integrally causal thing. There are two things. So, there should be P2 and Q7. These two are the state variables. Fine. So, we have asked this question and got this answer. Now, let us ask this question with reference to the C element. So, C7. What does it give to the system? Effort. Effort in C, in 7. So, E7. Express it in terms of the state variable, which you know. It is actually spring constant K Q7. Done. Now, ask this question with reference to the R6. What does it give to the system? It gives the effort E6. Can you see that? It receives flow and gives effort. So, E6. E6 it could give because it is received flow 6. So, first related to that. So, this is R F6, R times F6. Now, F6 is, then we have to find out where does the F6 come from. F6, it is connected to one junction, therefore, there must be a strong bond bringing in that information. Where is that? Here. So, this is equal to R F5. F5 is not a state variable. Where does this information come from? It comes from 3 and 4. And notice now we have to worry about the power direction, because power direction shows that F5 is E3 plus E4. Had the power direction been opposite here, which we could, then it would be 4 minus 3. So, now we can substitute here R F4 plus F3. F4 is known, it is the externally applied current source. Say if this current source is, say, V of t, we can write R V t plus F3. F3 is not state variable, but this information must be coming from somewhere. Where is it? Where does this flow information come from? Yes, this I element. Yeah, here is a one junction. So, therefore, there must be a strong bond bringing in that information, which is this F2. So, this is F2. Then R V t plus F2 we already know. Done. So, we have expressed the right hand side. So, notice how we did it. We started with the variable that it gives. It could give that information because it is received some information that is related first by this, and then we scout the whole bond graph to find out where was this information generated, and that is how we have arrived at this. This has generated that information. See how as information is generated in a whole system, it is not easily visible, but the moment you draw the bond graph, it becomes visible. You can see that the information channel by which it is flowing is like this. The flow information that this fellow has received was actually generated by this and that. That is how ultimately you express it. Okay. Now, let us go to the other things. What remains are the two flows, two sources. So, what does the source of effort give to the system? The effort. What does the flow give to the system? The flow. So, these are trivial. So, when this question is asked with respect to, let us block it, S E, then the answer is suppose this is F t and this is V t, this gives F t, and for S f it is So, these are trivial. So, let us not bother about that. These are the main information that it has generated. Now, let us ask the second question. What was the second question? What do the integrally causal storage elements receive from the system? So, there are only two integrally causal storage elements, one I2 and C7. So, let us first ask this question with respect to I2. Second question. I2. What has it received? It has received E2. It has received E2. So, it has received E2. E2 is nothing but P2 dot. Okay. So, we have the dotted term, we normally express that in the left hand side. So, we bring it here. So, is equal to E2, we can write it. So, we have got the equation, differential equation with P2 dot is equal to E2, but we do not know E2, and we have to scout the whole bond graph to find out where this information is generated. E2. E2 is a addition of E1 minus E3 because of this power direction. Okay. In this particular one junction, because of this power direction, E1 is equal to E2 plus E3. So, E2 we can separately write E1 is equal to E2 plus E3. So, we want E2 is E1 minus E3. So, we can substitute E1 minus E3. E1 is known, E1 is Ft, we substitute, is equal to Ft minus, now E3, where does that information come from? E3 is connected to a 0 junction, therefore, there must be a strong bond bringing in that information, which is this. So, E5 is equal to Ft minus E5, where does information come from? E5, yes, it is E5 is E6 plus E7, it is a one junction. One junction means it is a effort summing junction, and because of the power directions, E5 is equal to E6 plus E7. So, we can write E6 minus E7. Okay. Now, E6 is known, E7 is known, substitute. So, it is Ft minus E6 was R V T minus R P2 by M minus E7 is KQ7. Done. Equation ready. Fine. Now, just do the same thing with respect to C7. C7 is the other. Its state variable is, what does it receive from the system? It is F7. F7, we express it as P, Q7 dot, and then put it in this side F7, and then scout the bond graph to find out where this information come from. Okay. So, now complete that exercise, yourself complete that exercise, that here is F7, we have written as F7 is what is it's receiving from the system, and in the right hand side we have got the state variable which we bring to the left hand side. So, F7 is the thing that we need to find out. F7 comes from this one junction, there must be some place where it is a strong bond, it is 5. So, F7 is F5, F5 should come from somewhere. F5 is definitely this F4 plus F3, and F3 should be F2. So, it has come from here and here, just write it, you will get the differential equation. Clear? Okay. We will stop here and we will take up more examples in the next class. Thank you.